Good morning, Physics 30, and welcome back to our video lessons. So for this unit, we're going to be looking at electromagnetic radiation. So keep in mind, electromagnetic radiation, this is going to be your light waves. Okay, that's going to be the most common type that we know about. We'll be looking at the whole spectrum here. This is our third unit, the start of the third unit, and there are 2 chapters in this unit. So that means 2 assignments. And this is also going to be the last mandatory unit in which you need to complete the course during this COVID outbreak. So, however, though, I will keep that 4th unit, atomic physics, open, and I will allow you to finish that as well, but optionally. However, if you are going to be going and getting a physics degree, or if you're going to be becoming an engineer, or going to be taking a degree that has a lot of chemistry in it, I highly recommend that you do take that last unit because you will need it for those areas. But if you're not going in those routes, then I wouldn't worry too much about it. Okay? So we're going to be building a little bit on our waves unit from last year, but just a bit, because last year we looked at mechanical waves, and this year we're doing EMR waves, which behave completely differently, okay, in many different respects. So a few similarities, but mostly different. So for this guy, our EMR, we can begin. All right. So, ladies and gentlemen, Ørsted discovered that your electric current produces a magnetic field. Faraday discovered your magnetic field can produce an electric current. So we've already looked at those. However, Maxwell put the 2 together, and he came up with the whole idea of electromagnetic radiation, which is going to be our big focus. So your abbreviation is EMR. We're not going to be saying electromagnetic radiation all the time. Just too long. We say EMR a lot. Okay, so EMR waves, they can be produced from 2 different sources. An accelerating charged particle, such as an electron or a proton or what have you, or a changing magnetic or electric field. Now, if we still had a test, these 2 points would absolutely be on test, but we don't have tests, unfortunately. Darn it, hey? Okay. So, for example, with an accelerating charged particle, think about light bulbs, for example, like the old school incandescent light bulbs. So the tungsten filament has a higher resistance than the copper wire. So that the electrons are going to have a harder time going through that. So the electrons are going to slow down. And as the electrons are going to decelerate in that tungsten filament, it's going to start to glow, so producing your electromagnetic radiation. So, neat, eh? I think it's pretty cool. Okay. Now, your EMR waves, they're going to be made up of vibrating electric and magnetic fields that are going to regenerate each other. So they're going to rebuild each other back. That's why light waves can go on pretty much indefinitely until they hit something. Okay, so like for example, if we're going to look at a star that's 65 million light years away, well, the light that's coming from that planet originated from that planet or star at the time of the dinosaurs. Okay. So another thing to keep in mind is at any point in time, your 2 fields are going to be perpendicular to each other. So one's going one way, one's going the other. And a drop of pin. Be right back. Guess these videos aren't so different from class after all, hey? Well, at least the silly things I do anyway. That's not going to change. Okay. Now, EMR is said to be a transverse wave, okay, because our wave travel is perpendicular to our oscillation, okay? So what does that even mean, really? So let's think back to last year's Physics 20. You guys remember my epic dance moves, your longitudinal waves and your transverse waves? Yeah? I will show you my dance moves again because they're cool. You guys already know I'm crazy, so this is fine. Okay. So, for example, when we have our lovely transverse wave, the energy, your wave is going to be going like this. Well, the wave is moving forward. So, wave going up and down, well, energy moving forward. See? Doing the transverse wave. Whereas your longitudinal waves, the particles are vibrating back and forth while the energy is going this way. So your longitudinal wave dance move. Oh yeah, your longitudinal wave. I'm surprised you guys don't think my awesome dance moves are going to be the next greatest hit. I mean, really. Okay. So it's EMR is a transverse wave, so its energy is going up and down while the wave is going forward. Okay, energy is going this way, direction travels this way, whereas the wave is going up and down. Cool beans? Cool. All right. Now, ladies and gentlemen, all EMR travels at what we call the speed of light. So, and which is the value of 3.0 times 10 to the power of 8 meters per second. So when we say light speed, that's what it is. Now, keep in mind that's at speed in a vacuum. However, we assume this is also the case for air as well. However, if it's going to be going through any other medium, so it's going to be going a lot much more of a different speed. Now, some EMR can't travel through certain media. For example, radio waves, which are EMR, they can travel through brick buildings okay, which is why you can get radio signals inside your house. Okay, whereas X-rays, they can travel through that no problem, but they can't go through lead. So that's why when you go and you get an X-ray, they're going to give you a lead apron to wear over your vital bits, so your lungs, liver, heart, what have you, and then to protect them from the X-rays. Okay, so that piece is definitely important. It may come back to haunt you in the future or not. Okay. All right, so what we're going to do, ladies and gentlemen, is we're going to label a few things on our lovely EMR diagram here. So you can see here with our little label thing here that we have the 3 perpendicular lines. In this particular wave, the electric field is going up and down, the magnetic field is going side to side, and the direction of motion is that way. So we have 3 perpendicular lines here. Okay, so I'm going to do some labeling. Okay, I'll try to label these in different colors so they'll be a little bit easier for you guys to see. So something like all right, here's the first piece in your notes, as you guys can see in the list at the bottom here. I'm not going to be writing on this text list. You guys can read that yourselves. I will just be labeling what I need to on the diagram, and then I'll come back and highlight after. Okay, so the first piece we need to look at is your lambda, or your wavelength. So this guy here. Now, recalling from last year, the definition of a wavelength is the distance from one point on a wave to the equivalent point on the next wave. So here, we're measuring lambda from here, the top of the electric wave. The electric wave is going to go all the way down the bottom, and then it's going to come back up to the top again. I could also choose to measure one wavelength from, say, here on the magnetic portion of the field to here on the magnetic portion. Okay, so on this wave, that would also equal one wavelength. And we use the Greek letter lambda for that. So I can never draw it with the curlicues. I always draw lambda like a sideways T. Okay, so you can start at any point on the wave, but it's just generally easier to measure crest to crest, or you could measure trough to trough. Like you could measure from here to here, and that's still going to be one wavelength. Okay, and it's how far the waves are from each other. We measure wavelengths in meters. Okay. Your units for wavelength is going to be meters. Quite often with light waves, you'll be given the units in nanometers times 10 to the power -9. But what do we do with that? Convert your units. Absolutely. Okay. So what I'm going to do now is, just for ease of viewing, I'm going to erase all of these red lines. And then when we start talking about the source, I'll label that. Well, no, source is easy. I'll just label that in a different color. Okay, so the next piece in your notes is the source. Okay, so we can say if your wave is going this way, the source, okay, could be here. This is going to be your vibrating particles. Okay. So your electrons, if it's going to be producing light via electricity, your vibrating or accelerating particles, it's going to be having your changing electric or magnetic fields, okay? And it will be where it's going to produce that wave. Okay. Next thing, well, we don't need to draw the medium. Okay, the medium is just going to be what the wave is going to travel through. And this medium could be anything from air. That's going to be the most common one. But we could change the medium and say it could be a brick wall that we're going to be having EMR go through. Light waves can't go through a brick wall, but they can go through glass. And that change, as EMR goes through glass, its speed is going to change. So EMR can go through water to some extent. Its speed is going to change as it goes through water. That is going to be a very major concept later on in the unit, where we're going to be looking at diffraction and refraction. Okay, so that's going to be super important. Okay, so there's wave propagation, movement in direction of the wave through a medium. Okay, nothing crazy there. Okay, now these are the ones that I'm going to draw and label on. Okay, so we're going to go back up to our diagram and we will label frequency. I'm going to erase all this stuff now, so then that way we can go back and label stuff easier for our frequency. Okay. So the frequency, ladies and gentlemen, as you guys hopefully remember from last year, the frequency is the number of waves that are going to pass a certain point in 1 second. So if I set a little marker here, okay, and then I wait for wavelengths to go by, and let's say that if my marker has then still stayed the same, but this many waves have gone past. Well, we've had one wavelength go past a point in a second, and then we have had another wavelength go past a point in a second. Okay, so well, that's one. Oh, that's not quite a wavelength. That's half. So that's half a lambda. That's half a wavelength. So that would mean, ladies and gentlemen, that we have had a frequency of 1.5 hertz. Now, ladies and gentlemen, the frequency of bad physics jokes just hurts. Get it? No, it's an epic pun. An epic pun. All right. So, ladies and gentlemen, when you are finished laughing at my terrible jokes, okay, so the frequency is how many wavelengths are going to be going past a point in a second. Okay, so your unit for hertz is actually seconds to the power of -1, or it's going to be 1 over second, because we just don't really say, for this bit, we don't write number of wavelengths in a second, right? So we just say 1. Units are hertz. Okay, now let's look at period. Now, the definition of period, now this is the inverse of the frequency. It is how many, excuse me, is the length of time it takes for one wavelength to pass a certain point. So if we want the wavelength starting from here and then ending here, the time it takes from the start here to the finish here to go past this point here, that is going to be the period. Okay, so that is inverse to your frequency. And the formal unit for period, ladies and gentlemen, is going to be seconds. Sounds good? All right. So we're going to put a star beside these terms here, as they are going to come back quite a bit throughout the unit. All right, so ladies and gentlemen, this piece in your notes, and if you haven't found them yet, your notes are on Google Classroom, as these ones I hadn't given to you guys before the school's closed, so I will be giving you these guys notes section at a time with the video. So go onto your Google Classroom. If you haven't found these already, your notes are going to be in the same post as where you found the video, okay? Okay, so ladies and gentlemen, this EMR spectrum here is really, really important. If there was a diploma, there would be a lot of stuff for you to memorize on this diagram, because you will notice you do not have this diagram on your data sheet. I know it's something that Ms. K has been bitterly complaining about for a long time, and if we had a diploma exam this year, I would have been bitterly complaining about it at the government, that you guys have to memorize this stuff. Unfortunately, you do, but there is, as of now, there is going to be no diploma exams this year. So as of now, as in when I recorded this video, I don't want to say what's going to happen in the future, because who knows really at this point. The only advice I have at this point is just don't watch the movie Contagion for entertainment at this point. Okay. All right. So these bits are really important. The shorter the wavelength, the higher the frequency. So we'll be looking at an equation that shows this a bit later, and the higher the energy. So I wouldn't do a ton of drawing on this, or at least messy drawing, okay, because you'll need to look at it a lot for your assignment and your questions. But I'm going to do some labeling here. So the higher the frequency, the higher the energy. So I'm actually going to label this up here. So that's supposed to be an H. These guys are going to be high energy waves, and these are going to be low energy. Okay. So you have your wavelength down here, and you have your frequency up there. So the longer the wavelength, lower the frequency, lower the energy. Okay. So other things that you are going to need to memorize, if there was a diploma exam, you would need to memorize the frequencies and the wavelengths of each of the categories of electromagnetic radiation. Because we don't have a diploma and because we don't have exams, do not memorize this chart. However, if there is a diploma exam, and if for some reason, heaven knows why, you'll be getting a test on this, you do have to memorize it. Okay, so just keep that in mind, okay? And you are also, other things you're going to need to memorize as well, assuming if there is a diploma, are the wavelengths of your colors as well. In your notes that I've given you, I don't remember if this is in color or not, but you have no, it'll be in color. It'll be in color. The stuff I've given you is the same document here, so it'll be in color. So you will have this in color. If you want to print it out to make it easier for you, you can do that too. If there was a test, you would have to memorize this spectrum as well. So the different ranges for your different colors of EMR. So this table is going to be hugely important. You will be able to come back at it many, many times. Heck, even print off an extra page of this and staple it to your data booklet. That would be a really good idea, guys. Okay, but what it will allow you to see here is the different categories of EMR and their different wavelengths and frequencies. So radio waves, what allows you to listen to your jams, has a frequency of about up to 10 to the 8 hertz and about 10 to 3 hertz. Well, its wavelength is going to be quite large. So right here is your 3 to the power of 4 meters, all up to 3 meters. So quite a range. And these are big waves. 3 to the power of 4 meters, ladies and gentlemen. It's like 30 kilometers. Okay. And then All our famous light waves, what we actually see, what allows us to see these wavelengths that travel through the air, hit your rods and cones in the back of your eyes, converting into electrical signals, which then we process in our brains. Those of you who took Bio 30, especially with me, I hope you guys remember occipital lobe process is at the back where we see all the vision. And just to freak you guys out a little bit, the EMR that we are actually processing is really a teeny tiny slip of data here. It gives us a very, very minor vision of what's actually happening with EMR in the world. So heat can be detected with infrared. A lot of stuff that it's warm or hot will be emitting infrared radiation. We can't see that, ladies and gentlemen. Although some pit viper snakes can. That's what the pits are. They can detect infrared radiation. Pretty cool. Okay. UV light, we can't see this either. It burns our skin, but we can't see it. So a little bit of Latin. Infrared. Infra means below. Ultra means above in Latin. So infrared, wavelengths that are below red. Ultraviolet, above violet. Okay, neat. They use that with frequency though. Okay, so you'll be able to just read the charts for your x-rays and whatever radiation you want in order to get your data off of this. So use this a lot. Okay, spend a lot of time with it for your assignments. Just have it around and use it to answer your assignments. On a test, if there is one, you need to memorize it. I know, it sucks. It's the same way I've been bitterly complaining for years about the Chem 30 diploma and your lack of data sheets. Okay. So, ladies and gentlemen, monochromatic light. Mono in Latin means one. Chrome is color. Okay. So this is light that consists of just a single frequency or wavelength, so one color. Okay. So that'd be red light or blue light or what have you. Now, white light is not monochromatic. It consists of a whole bunch of colors, frequencies, and wavelengths. That's actually how we detect color. Most light sources that we see is white light. However, the fact that the sleeves of my hoodie appear black is because they are absorbing all frequencies of that visible light spectrum of EMR. The reason why the St. Joe's lettering on my hoodie appears white is because it is reflecting all visible light wavelengths of EMR. And why the SJ logo on my hoodie appears green is because it is absorbing all frequencies of light and then reflecting green. The green light that is reflected is then picked up by the cones in our eyes, turned into electrical signals, which runs down your optic nerve to your occipital lobe, which we then process as green. So, ladies and gentlemen, color in the universe does not actually exist as we see it. It exists as EMR, alternating magnetic and electric fields in a wave. So it's our brains that are telling us what the colors are. So how do we really know that, well, when I say that the ink on the pages that I wrote is red, well, how do we know we're actually seeing the same thing? How do you know that what I see is red, you really see as green? I would have no way to tell if that's the case. That's a whole different level of psychology called perception and reception and perception. It's cool. Very cool. Okay. Reception versus perception. Okay. So off the bio, back to physics. Enough of messing with your minds today. Okay. So, ladies and gentlemen, the formulas for wave theory. There's a bunch of formulas that we're going to be looking at. Some are going to be for general wave theory, which you'll have seen before. Some are going to be from few new bits. Okay, so ladies and gentlemen, we've got two theories that we're going to be looking at in this unit. We have wave theory, so classical physics, and particle theory, which is quantum physics or modern physics. So it used to be thought that light waves, and EMR were all pure waves. Well, not exactly, because sometimes they can be explained by both particle theory and by wave theory. So this is called wave-particle duality because sometimes light can be measured as if it was a wave and sometimes it behaves as if it's a particle. So it can be kind of confusing. So in general, once again, I'm never going to say always, or very, very rarely going to say always. High frequency, okay, low frequency is going to be treated as a wave, and high frequency is going to be treated as a particle for the most part. Okay, so the first part, we're going to talk about wave theory, and the second part of the unit, we're going to look at particle theory. Sounds good? All right. All right, so equations for this, ladies and gentlemen. We have your universal wave equation. So this guy here will work for pretty much any wave, where your speed is going to be in meters per second. Now, this is the difference from any wave. EMR is always going to have the same speed. This is on your data sheet. It should be on the very back page in all those lists of values that you have. Okay? Back page of your data sheet. Okay? You do not have to memorize this. If anyone has taken Science 30, then you will have absolutely already worked with this equation. Okay, now F is your frequency in hertz or seconds to the power of -1, and lambda is your wavelength in meters. Okay, it's a pretty easy equation. This equation, our next one here, this is one that we looked at last year, so I hope this looks familiar to you. And T is the period in seconds, so that is how long it takes one wavelength to travel a certain distance. Okay, so the time it takes for one wavelength to pass a certain point. Frequency is going to be your hertz. Okay, and they are the inverse of each other, so we could even write this like that as well. Okay. And our next equation, ladies and gentlemen, is EMR is going to travel at a constant speed. Key piece, constant speed, so long as it's in the same medium. If it's in a different medium, it's going to change speed, and that is where we're going to get the bending of light. Okay. Now, V, once again, speed of light. Okay. All EMR is this speed. Okay. D is your distance that it's going to travel in meters. Time, how long it takes in seconds. Use that equation lots. All right, so we're going to look at a couple calculations. Nothing nearly as tricky as some of the stuff we've done so far. So this is a bit of a calculation break for you guys. Okay. So a star explodes. Yeah, supernova. And it is that many meters away from Earth. That's a long way from Earth. So you have our distance of 9.85 times 10 to the power of 26 meters. One thing to watch out for, ladies and gentlemen, is notice that your wavelength and your distance are going to have the same units. So you have to be very, very cautious about that and pay attention to how the question is worded. So this many meters away from Earth, well, that's distance. You're not going to have a wavelength of that size. How many days would it take the light from this star to reach Earth? Well, key words. Light, ladies and gentlemen. The second you see the word light, it means it's going to be a category of EMR. Now, your speed of EMR from your data book is 3.0 times 10 to the power of 8 meters per second. Okay, so, well, how many days? You've been asked to find time. Well, this, ladies and gentlemen, I can get time in seconds. So therefore, I'm just going to have to convert my time afterwards. Because the tricky part about this question is we just have to remember that it's going to be traveling at a constant speed, unless it's going to change mediums. Okay, it's in space. There's not really much of a medium for it to go through in a vacuum. So, should be fun. Okay, so I'm going to rearrange our equation. Plunk our numbers in. If you guys notice, I'm getting way better at writing with this thing. I'm very pleased with myself. Okay, so we're going to get this time in seconds. So 3.283 repeating seconds. So because the question asked us for our units in days, we are going to need to now convert our units. So let's do some unit analysis. Okay, so ladies and gentlemen, how many seconds are in a day? Well, as opposed to finding that out, let's go the easy route. How many seconds are in an hour? 3,600. Absolutely. So we want to cancel out these seconds, ladies and gentlemen. So 3,600 seconds. And then we need to, so we have our, 1 hour. So now we have our time in hours. And now we are going to need, we have our units in hours. We need to get rid of the hours. And there are 24 hours in one day. So you're going to wind up with 3.80 times 10 to the power of 13 days with your 3 sigdicks. Okay. So, ladies and gentlemen, that's a long time. It's a long time. So, like I mentioned earlier, if a star was shining light towards us, that light we're seeing in the sky could be millions of years old. And some of these stars, that the light that we are seeing, they've already exploded and gone. They're dead. They're dead stars. So the light from them that was released by them while they were still alive is still going. So, isn't that awesome? I think it's pretty cool. Okay. Think of it as their legacy or something like that. All right. Next question. So blue light has a wavelength of 460 nanometers, and a red light has a wavelength of about 720 nanometers. Now, assuming I didn't give you this in a question, where would you find this info? That's right, the table in your notes. That diagram in your notes that has all that lovely EMR spectra on it. What I recommend you do is that you guys print out a separate copy of that and just staple that to your data booklet, so that way you always have it and aren't going to have to fuss through papers trying to find that page. Okay. Now, A, which color has more energy? Now, that's a theory question, thinking back to your notes earlier. Blue light, ladies and gentlemen, has a lower wavelength than your red light, which has a larger wavelength. So if blue has a lower wavelength, what's its frequency going to be in comparison to that of red? Good, it's going to be higher because they're inverse to each other. So I always like to memorize it in the way of the higher the frequency, the higher the energy. I find that easier to remember than lower the wavelength, the higher the energy. So I always mentally make the jump of, okay, well, the wavelength is lower, therefore the frequency is going to be higher, therefore the energy is higher. Okay, so your answer is blue light, because remember, 3 inverted dots in a triangle, or 3 dots in an inverted triangle means because. of the lower wavelength or because of the higher frequency. Okay, so whichever one you want to go with. Okay, B, calculate the period of the blue light. Okay, well, we know that the period is the inverse of the frequency, and the information that we have available to us for the blue light is our 416 nanometers. That's supposed to be in them. Okay, well, we need to convert this, ladies and gentlemen, into meters. Never, ever, ever do your math in nanometers. Okay, so we're going to multiply that by our 10 to the power of -9. And we're going to wind up with your 4.6 times 10 to the power of -7 meters. Well, I need to get the frequency first before I can calculate the period. Well, how am I going to get the frequency? I don't have any other data. Or do I? What's that other piece of data you have? That's a constant. That isn't going to change. Good. C is another symbol often used to represent the speed of light, or it can be V. Either way, it doesn't matter. You have the speed of light. That is a value that is a constant and you will always have. So we can now use this equation. So V is equal to frequency times lambda. Well, we have lambda. We have the speed. We can find our frequency. Plonk in your numbers. And throw it in your calculator. Now, calculator tip again, ladies and gentlemen. I recommend entering these values into your calculator as 3, and then hit that yellow second button. And then if you hit the wonky comma button with the E on top of it, and then -8, then you're going to divide that by your 4.6, and then your second, and then your little comma with the E above it, -7. Is if you do this method, then you don't need to worry about your brackets. If you're going to enter 3 times 10 to the power of -8, you must put brackets around each of those values because you're not telling your calculator, I want this in scientific notation. It's just each individual steps. So if you don't put your brackets, you're going to get a calculator error. So watch out for that, please and thank you. Okay. So you're going to get a frequency, ladies and gentlemen, of... Oh, I did this differently. Hold on a sec. My notes earlier. I just derived one big old equation and didn't actually calculate the separate frequency, but for some reason I decided to do it differently now. Okay. All right. So we're going to take our 3 second E8 divided by 4.6 second E -7. So this also gives me the opportunity here to show you guys what it should look like when you're using those E's. I know it's backwards. I'm sorry, guys. I'm not quite sure how to get it to the camera to flip backwards. So it actually is proper orientation. Okay. So your frequency is 6.52 ... times 10 to the power of 14 hertz. Now, ladies and gentlemen, this is also a common mistake that I see. Just be aware. I see a lot of people who will just write down this bit and drop the E14 at the end. So notice at the very end you have that E in your calculator there. That E is times 10 to the power of. So don't drop that. Okay, if you drop that, you're going to get the answer wrong. Okay, so be aware of that. So now we have our frequency, and now we're just going to take the inverse of that, and that's going to get the period. Using all the numbers in your calculator. And I'll show you a shortcut actually on your calculator. You guys see this button here? That x to the power of -1 button? That button means take the inverse of. So instead of going 1 divided by second answer, I'm just going to hit that inverse button. And it'll give me my answer. Okay. So your period, ladies and gentlemen, is 1.53 repeating times 10 to the power of -15 seconds. Okay, let's double check and see what sig digs I want. I want 3 sig digs, so I just get rid of that repeating essentially. Okay. So, ladies and gentlemen, one thing to be aware of, one final piece. This unit, we're going to deal with really, really big numbers and really, really small numbers. Big frequencies and small wavelengths and small seconds. So if you wind up with numbers that are really huge and really small, that's going to be okay sometimes. So let's think logically for a second. While we're dealing with how long it takes for one wavelength to pass a certain point. Well, we're talking with light here. Light moves ridiculously fast. It's not going to be much time at all. So that makes sense to have a really tiny amount of time. Okay. So, ladies and gentlemen, what you guys can do now is chip away at some practice problems down there at the bottom. And we will talk to you guys later. Have a good rest of the day and no fires, injuries, or explosions. Now I can't find the off button. There we go. See you guys later.